Welcome to the last session of the Wednesday, first day of the North American Steel Construction Conference. Today's presentation is on ASCE E17, design loads during construction. We have two speakers, Dave Ruby and Jeff Gasparat, who will be addressing the topic. My name is Sylvie Boulanger. I'm with the Jacques Cartier and Champlain Bridges Incorporated, so for you it's like a bit of the Montreal Port Authority. And I'll be moderating the session. Please note the PDH code, which is 87373. It's not the same on the screen, so I almost got caught there. So it's 87373. I'll be presenting the bios of the two speakers, and without further ado, I will let them come up and present the topic. Dave Ruby completed his engineering degree at Rensselaer Polytechnic Institute. Upon graduation, he joined the American Bridge Division of United States Steel in Ambridge, Pennsylvania. Dave played a key role in iconic structures such as the John Hancock Building. I had the opportunity to see a talk by Dave, which was just incredible. The Willis Tower and the Aon Center. He later founded Ruby & Associates, where he currently holds the position of chairman. Dave has received several outstanding awards, including the AISC Lifetime Achievement Award. He also serves on the AISC Code of Standard Practice Committee. Dave is the author of AISC Design Guide number 23, Constructability for Structural Steel Buildings. So I've got a page caught here. Jeff Gasparat completed his bachelor's in civil engineering from Michigan Technological University. He is a licensed professional engineer in Michigan. During Jeff's long tenure at Ruby & Associates, he has become a specialist in erection engineering and has had a chance to be involved in what he considers to be some of the most interesting projects in the United States that include stadiums, arenas, performing arts auditoriums, space vehicle launching towers, convention halls, bridges, and historical theaters. So without further ado, Dave, would you come up?
Thank you, Sylvia. Appreciate it. I want to understand this afternoon, gentlemen, I am not here as an expert. I have stubbed my toe more than enough times I can count. And we are not representing ASCE. We are not critiquing ASCE. What we're attempting to do with this particular document is to focus on the fact that how do you use it, or how is it used in structural steel erection? Because if you spend any time reading it, it has areas that cover that, but not quite directly, and it looks at things a little differently, very much like you would look at it if you was in the concrete industry, is the way we believe it's been done. So we understand it's a source, but what we're really issue at Quinamin is when I was asked to do this from Sylvie, and I actually was asked to do this 2 years ago. I was supposed to make this presentation, but I took a kind of a detour last year through the prostate, and so I'm back in the living. And when we did this, we looked at it and we said, well, the loads are wonderful. Wind loads, dead loads, live loads, whipping loads, what you pile on the floor, all those sorts of things. But really what the issue would be is, when do you apply them? How do you apply them? What allowable loads do you use? Do the AISC specification govern that design? Are you obligated to be designed for 0.98 and can't exceed? Can you use a 33% overstress for wind? There is no guidance for that. As an erection engineer, you have to make those decisions. But the second thing we go back as an engineer that's designing a building, understand that the engineer who's doing the erection, he needs as much information about the design as possible, because your permanent lateral load bracing system may not be there. The sequence with regard to the way you would like it designed or like it built may not happen because the contractor has his trailer parked on that end of the site, so you're going to start at another end of the site. There's all sorts of things that involve this element, and we can talk about the loads, and you can read that probably in about 45 minutes. But in fact, how do we apply them? When do we apply them? Where are they applied? Why don't we apply? What's the issues? And those sorts of things. We're going to try to talk about that somewhat today. In addition to that, we're going to be talking about what we What are the goals? Would try to be some understanding of this. And the first thing I would say to you is that it says design. Now, those of you here are engineers. What's design mean to you? Do I have to? I'm sure I don't have to tell you, but the design is what you would expect the structural engineer of record would be using to design the building. So this title of this product, of this book, is Design Loads for Construction. And I'm saying, yeah, I don't think it's quite design. As an erection engineer, I might use it to do a design check. I might do it to make some decision as to what shoring I may need. I may use it to use some decision as to whether members need to be resized. But is it design? Is it code mandated? No, it is not. We're going to look at then what happens when I'm talking about what are all the other things. Well, then below that document of A3714, we have governance. What's governing that? What are the codes and specs, what the code and the specifications, whatever's put on the drawings, industry guidelines, project requirements, and then we're going to finish up with some wind and case studies with regard to that. And all of this has to do with, we've got the book that says these are the loads, but as I said, doesn't know when to apply it, why to apply it, what are the issues. But a little history. ASCE sort of an 02 indicates for some configurations, and I think everyone knows this, the loads on a structure during construction may exceed the loads on the finished structure, and hence will govern the design of the structure. Well, I would need to tell you that in the 3714, that paragraph has been deleted. And they talk about members may need to be resized and things may need to be redone, but they don't define and use the word will govern the design of the structure. I personally believe that that in fact is reasonable, because I think it's unreasonable to assume that a structural engineer, when designing the building, is going to have any clue on what's going to take place in that structure during erection. And the issue gets to that, well, and we have this, probably 25, 30, 40% of our work is erection engineering. It's a lot of fun. The difference being is that when you design a building and you've made your model in whatever GT Strudel or whatever it is, and you push the button and run, and it comes out and you check and see you got blue and green and the building's fine. But when we build it, one piece at a time. And each piece has to be stable. Each two pieces have to be stable. So we don't run that model once. We may run that model 100 times with an additional member, an additional member. So there's a whole different, and what doing because of that, at the end of it, I would say we know that structure and how it reacts, maybe even better than the original engineer, because we've had to make that, and along that situation, when we do that, we have to develop that mystic thing that seems to be left out of most educational data. It's called load path. And we can't build it. Stability can't happen if there isn't a load path. So when they stated this from that, 13, let me get the budget here. Okay, did it go to sleep on me? Oh, it's not moving forward. What do I, let me see here. I just did, that came up. Try that. Try that? All right, there we are. Thank you, Jeff. There's always reasons to have the younger generation around. In many cases, that's that part that they talk about integrity that I just gave you that was in 2. What's in 14? Ah, yes, a little smarter. In many cases, stronger members and connections than originally designed for the permanent structure will have to be provided to support construction loads. Duh. Okay? Yes. So they brightened up between it. But I think the focus when they first did this in 2 was they really were trying to provide the fact that there was design information necessary and there was work necessary. When you do construction loads, there is additional engineering necessary. I think that was their focus. But that paragraph was written, and in the design of the structure, boom, that's The attorneys probably were all over that puppy. So what we're going to try to do is I'm going to try to go through these things in reasonably smart. You may have questions. Actually, by the way, you can interrupt any time. I have no problem with that. We're talking about governance. We were talking about ASCE 37, but governance, OSHA tells the ironworkers what you have to do. One of the things they tell the ironworkers, they have to have 4 anchor bolts. Engineers, they have 4 anchor bolts. Now, I would suggest they not be 6 by 6 in a pattern. I would suggest they be a little smaller outside, but in fact, they need 4 anchor bolts. So it primarily impacts that, but it is governance of the erection and how the loads are applied. We get to the purpose of ASCE 17, which actually is the design loads that the structural engineers use in the design of the structure. And you'll see that this is the purpose and the basic. They're talking about strengths and serviceability and strains, etc., which are very similar to what we're going to talk about on A3714. The purpose is to provide minimum design loads, they use the word, requirements for construction of buildings on structures. And we're going to talk to them already. We've had some conversation with ASCE 7 concerning this term of design. I think it's the wrong word. I'm not sure what the word should be, but the inference is that it could possibly be code required, although it is not referenced anywhere, and it could be, somebody could say, the owner could tell to you, hey, why do I have to pay this fabricator so much money to reinforce its structure since you designed it? But on the other hand, if we were building a bridge, that's exactly what would be done. That structure would be designed for a particular erection sequence, not recommended, but one in which it is based. And so today, when we look at a typical 10 or 15 or 20-story building, that's not an issue. But when we're looking at an arena or a stadium, or the canopy over the Miami Dolphins Stadium, the engineer, the erection engineer, needs to know everything about that structure in order to build it. Needs to know that. And in fact, in some cases, we were talking, those members, those type of structures do have members that are reinforced. And the question is now, what do you shore? Do you shore? Where do do you preload? Do you pre-erect? There's all sorts of things that impact that temporary issue that is not covered in this design loads. I'm saying, well, we do it so much, I guess we get used to it. But this standard does not specify the parties that's responsible. It doesn't even specify that there should be someone responsible for supervision in the field to see, in fact, that it was called out. Now, I'm not suggesting that that should be there. I'm just telling that that's what it specifically states. It is not. It also, very interesting, it's intended to be used by a structural engineer that understands structure. I'm going to come back to that again, or probably repeat it, because there's a couple of other places in here where in the commentary they are suggesting to you how you should or could avoid stability issues in the field. And I'm saying, well, if it's intended for structural engineers that are knowledgeable in structures, why am I dabbling in that part of the document? Partially completed structures and temporary structures shall possess sufficient integrity under all stages of construction to remain stable and resist. Now, I appreciate the fact that that's here, and the reason why is this document covers timber and wood and timber and wood. I think they're similar. Timber, maybe it's laminated wood, I meant to say. Or concrete, or precast, all those sorts of things that goes. But if we're talking in structural steel, my feeling is the Code of Standard Practice is much clearer with regard to what's required for stability. In the commentary, however, this is what they're telling you. Now, we're talking about people or engineer. This is intended to give you to someone who actually understands structure. It says, sequencing the construction to avoid creating vulnerable, partially completed portions of the structure. Completing the permanent lateral load resisting system as the dependent portions of the structure are erected. That would be interesting if you're lateral load resistance was concrete block, and you couldn't put it into after the structure was built. I'm not sure how you would do that. Avoiding conditions that result in loads that exceed capacity of structural. I'm saying I don't understand these notes in this document if it's primarily to talk about design loads. I'm missing that point. Not that it can't be done, but that's in. It says now in this case very similar to the portion of the document in 02 that was eliminated. In many cases, stronger members and connections that originally designed will have to be provided to support their construction loads. Now, the one element that, in fact, I have the most conversation with erectors about is many structures experience higher wind loading on the open structure than on the completed enclosed structure. I would change the word many to all. We just completed the erection procedure for the canopy over Sun Life Stadium, which is now called Hot Rod Stadium for Miami Dolphins. It's a canopy. It's supported on cables. It is completely sheathed, top and bottom, and covered all around. So in the final design of that, and in the wind load tests on that, it acts somewhat like a wing. When you're erecting it, none of that siding's there. Wind load on the erection, possible. I mean, we didn't have it, but if we designed it for the design loads at that point in time, was 12 times the design load that the structure was designed for. Now, the issue would be likely we weren't quite in the hurricane zone, so we came back from that and we backed down on several of those elements. But in fact, to literally brace that structure for the winds that could possibly happen during construction, there was nothing to brace to that was strong enough to hold it up. So they don't necessarily always apply. And on that particular thing, we sat down long and hard and talked to the erector about what we were going to do, and they did constant monitoring of the temperature, of the weather 200 to 300 miles away, when the winds were coming, et cetera, with regard to it, because we had a lot of cranes there with way up pictures up in the air, and we didn't want anybody injured or damaged. If we had a structural damage because of the winds, then we would, because there was no way to hold it back. But what are the types of loads out of ASCE 37? We have dead load and live load and construction and environment and lateral earth resistant pressures and forces interaction because of the partial parts of the structure and temporary supports and effects of loads created by methods and sequencing of construction. Okay? But not noted in there is design concept or the unique installation requirements that are necessary for the structure to be put in place, which would in fact temporarily impact your loads, as to whether you have to have preload or set things to a certain elevation, to an elevation that perceives to a point that as the dead load is put on it, it comes down to a final elevation, as opposed to setting it to an elevation and letting deflection go where it is. There are times where we have had to set a structure above and let it come down as load was put on place. This happens to be a picture, a shot of the Miami Dolphins Hard Rock Stadium in Miami. That truss is 190, I think it's 190 tons on each end, 360 tons total. We've got two of Manitowoc's largest cranes on one end and two Manitowoc cranes largest on the other end. That assembly was assembled about 100 feet from that final position, and then those four cranes walked. So if you are interested in wanting to know how much time you want to know and when the wind is going to be and what the floats are going to do and what the world is doing and is it tilting and is a surf up, you need to know all of that before you are ready, prepared to do this. Codes and specs. Well, we've got the IBC. It references ASCE 360. ANSI says maintain stability of the structure at all times. You'll understand that ASCE 37 has not introduced anything new. They're talk about stability. We've had it there for a long time. Stability in the general stability specifications in ASCE 14th edition. The frame of the structural frame shall be carried up true and plumb with the limits of the code of standard practice. As erection progresses, the structure shall be secured to support dead, erection, and other loads anticipated to occur during the period of erection. This becomes an issue with regard to where do those loads come from? When are they going to be applied? Are they coming from non-structural steel elements? Are they coming from precast that'll be erected later? Are they coming from wall panels that'll be put up in place? How does the erector know what that is? And so if in fact those sorts of loads will be coming on, they'll need to be told that. But one of the things on the Code of Standard Practice Committee, actually I've just walked off after about 10 or 12 years, but the one thing we have in there as a note is that the structural engineer is to define the lateral load resisting system. And why is that? Not because we want to know whether the structural engineer knows what the lateral load resisting system is and it's just a test for him. That's not the focus. The focus is that if I'm erecting it, what is the lateral load resisting system? So that as I erect it, portions or parts of it or whatever, that I can physically use that as part of my bracing system. Which means there needs to be a lateral load system with a load path that distributes to the bracing. Whether it's moment frames or whether it's X bracing, or whether it's precast panels or poured in place concrete or masonry walls. Now I've had a couple structures we've looked at that have fallen down. The masonry walls, which were the lateral bracing system, were shown on the architectural drawings. Not mentioned on the structural at all. It was a church, nice churches around columns around the side, nice peaked roof going up to a nice compression ring at the top and a little nice tension ring down at the bottom, and they put that puppy up there, but there was nothing where the tension ring was. There were supposed to be shear walls to take the load to the ground. There weren't any. So when they put the first two compression members up, they worked, they were there. And then they brought the second one up to head to the compression node, and it was too long. It was above the compression node. So the superintendent said, let's bring it down and check the dimensions. So they bring it down and set it down over here to take the dimensions, and they look at the drawings, and whoosh, that roof went down. Just unzipped. Well, there was nothing on the structural drawings to tell him who he was, right? And I'm saying to you is that that's part of what its lateral load resistance system is. Why do you want to define that? And why we ask for that? Any special conditions on your erection? Or what schedule there will be if in fact you were going to have precast or walls or non-masonry walls? What's the schedule for when they're in place? Now, why am I talking about all this when we're really supposed to be talking about loadings? Because, in fact, all of those impact the loads I will put on, when I put them on, how I put them on, and how I adjust my temporary bracing system. So I'm saying there's more to it than just having a book to pick the loads out. The erector needs not consider, these are more interesting comments, you do not need to consider any erection that results from the performance of the acts of others. In other words, when you're bidding that, I got an erector, he's chuckling because no one ever tells you when you're doing it, but when you're building the building, and let's say the exterior is precast, that's going to be the lateral system, and it will be the lateral system when it's completed, but the first 15 to 25% puts up, it doesn't provide any stability to the building, and it runs one hell of a lot of wind load, and it becomes a sail, and you have the structure and you have to hold it up, and you didn't know anything about this when you bid the job. So the erector not only need to consider that are unpredictable, like hurricanes, tornadoes, earthquakes, explosions, collisions, but in fact you can be requested to have a hurricane plan. We had a hurricane plan on dolphins. We had a hurricane plan in Puerto Rico. What's the hurricane plan? Something reasonably that you can work up, be prepared, that you can probably install in maybe a day, maybe two, but you're going to be monitoring the temperature, you're going to be monitoring the winds, you're going to be monitoring the weather to make sure that that possibility is. Temporary supports that are required during the erection of the steel frame, support caused by non-structural elements including cladding, all of that sort of thing. Those are elements that the erector needs to understand what he has to do, because it's a cost to him. And it's a load. Now, this is ASCE design examples, which they have helpfully, and they're really very, very, very helpful. But the original design base shear for this structure, wind, based on ASCE E7, it's 168 kips. If we look at the bare structure, 602. Now, what happens in that 602, that's considering the whole frame is bare. But if, in fact, I put a layer of deck at the second floor and the third floor, what I do then is I start to provide dead air on those beams. And so when the wind goes between the second floor deck and the third floor, the wind goes under those beams and it misses them, flows right through. And when the metal deck is off there, it catches every one of those beams. And so what happens here's then is the likelihood of us having to brace it for 602 kips. Yeah, not reasonable. But to understand it, if you take it by the letter of the way the documents are written, that's what you would have. And that's in that design example. Structural integrity. Partially completed structures and temporary shall possess sufficient. And we've talked about the stability again, but I bring it up because, in fact, stability is the issue of this whole document. Although it says loads, its stability is really the primary concern of this document and why it's generated. And they talked about the fact that it's not stable because of winds, but in fact, it may not be stable because it does not have a lateral load resisting system, whether it be temporary or permanent. Now, we talked about this on planning, etc., and I thought I would go back in the archives. This happened last century. I was with American Bridge when Hancock was built. I spent, I think, 4.5 years on this structure with SOM during the design process. But when we built this and we first sat down with the general contractor and the concrete contractor, there was a meeting decided as how this was going to be scheduled, because we had four cranes on this all around the outside, so we could, in order to get not necessarily reach all the areas in general, but it was more like how many pieces, volumes could we do, and we were shipping it in segments, and they were being furnished by different fabricating plants, and so we didn't want the fabricating plants trucks going to the north side or the south side or the west side or the east side. I mean, this plant would go north side, this plant would go south side. We're not, so it wasn't confusing to them. But anyway, we sat down and worked out a procedure with regard to it, and American Bridge generated the procedure for steel. This is what we're going to do, how many floors a week. And the concrete contractor looked at him and laughed. He says, "We're going to push your ass off the building." Well, how many of you here are associated with ironworkers? Have you ever challenged that ironworker? Did you lose that challenge? Guess what? We were 22 floors above the finished floor on that structure. We ran right away from them. And that superintendent, he did everything he could to make that concrete contractor eat those words, man. Don't ever tell me you're going to push me off a building. His name was Tex Twining. And it's a little side story. I could guess I said the first column that was set on this structure is a corner column, 165 tons, I believe, sitting on a 42-ton base plate. And it's at a double bevel on a corner. And it's a piece that's up in its wing. It's got gusset plates going on the east side and gusset plates going on the south side to catch the diagonals down on the bottom. So we're there for this first piece. The governor's there, the mayor's there, the city council's there, there's a whole bunch of people in this table, etc. And this truck pulls in. Well, that was simple, but truck pulling in, there wasn't room for 2 cranes in that area to unload this truck because it's an unbalanced load. You had to pick from both ends. So the one crane was in front of the truck and the other crane is behind the truck. And they pick it up, and then the truck drives out. And then the crane on the front end starts to pick it up, and the back crane walks it in, and we get it up to a point now that we have a double hitch. We had a hitch for lifting it, and then we had a hitch that once you attach, the column would slope to the two, 5/16 and 12 on one side and 3/8 and 12, I think, on the other side. So that would set that column and set it down just like we're talking in. They did that in about 45 minutes. So everybody applauded and all this good stuff. So I went up to Tex and I said, Tex, I said, that was incredible. He said, you know, I said, you set that thing like, he said, it looked to me like you'd set that before. Well, this was in 1966, and I am, how old am I? 28, I think. And he looked at me and he said, let me tell you this much. I am not going to let some engineering that some wet behind the ear engineer did make a fool out of me. We set that crane, we set that column at 4 o'clock this morning. Put it back on the truck and sent it out of town. Now, in Chicago, that load, that truck, that tonnage cannot be on the roads after dark. Can't be on the roads after 6 o'clock. Can't be on the roads before 7:30 or 8 o'clock in the morning. And they sent that son of a brick at night. And then sent it back out of town. And it came back in, and they just went through their motion, and it just went, put that thing in place. Don't ever challenge an iron worker. Industry guidance. ASCE supplies a fair amount of guidance. We have the erection bracing on 10. We have the constructability of structural steel buildings on 23, and stability of steel structures in 28. And those elements are all very, very helpful with regard to your erection, your temporary bracing, how things would be done, and how you would apply your loads. Project requirements. Well, what are project requirements? Project specs, general notes, bad dreams, framing schemes, special and unknown, super elevation, we don't know what, I mean, elevation or even deflection control, shoring, jacking, all of those things in one way or another can impact the magnitude of the load, when it's a load, how it's a load, and how you're going to take it out and the final structure. One general note like this: the structure is stable only in its completed form. The lateral load system consists of metal deck diaphragms, exterior. It gives you all that information, gives you not enough data. Even with that information, you don't have enough data to do the project. But that's the general note, right? The engineer feels he has done his part. He has finished the drawing. The drawings are done. That's his life. That's finished, okay? My feeling to engineers is you don't feel that way. Your drawings are garbage. They'll be good for making fire later. The function here is the completed structure. That's the project. So what you have to do is provide the data to do that. Whatever that is, you have to figure a way to provide that, okay? The contractor is not the enemy. Fabricator and erector are not the enemy. The question would be is, if you tell him what he needs here, the contractor is responsible for stability. He knows that. He knows that. But this up here, they're talking about all this stuff is, what's the schedule? When is all that stuff going to be in place? How long can I rely without, I mean, there's, anyway, I don't want to. Steel framing. And I don't have enough room to put down all the different steel. What I'm just saying is the type of steel framing there is, how it is, what it is, where it goes, where its availability is, the job site conditions, is there access in, there's access out, all of that is going to impact the loading, temporary bracing schemes that you put on the structure. Shoring. This is in Pittsburgh, the igloo. It's been torn down. That elevation out at that tip out there had to be maintained, but actually had to be set at an elevation so that as the structure, as they got all the load in place and they could bring the shores down, then the movable leaves would be able to be moved and they wouldn't be binding, etc. Significant elevation control in that process. Kansas City Performing Arts Center is a structure within a structure. They are outside of each other, and they had to be separated, but yet when in erecting them, you didn't have stability. You had to use the inner structure to support the outer structure, and we had this jacking frame added in there to be able to get to elevations. Super elevation. In Chicago, if you've not been there, this is what I usually demonstrate is that a wrinkled piece of paper that has been generated to look in stainless steel. But that is supported by 150, 250 tons of framing in behind it, with a cantilever like 100 and 125 feet, but the backspan is like 50 to 60 feet. Now, that's not the geometry you would like to see, but that's the geometry that there is. Now, when they did this particular beautiful thing, they had this done in CATIA, and all of the geometry was there. And the engineer had indicated in the specifications that the structural steel support shall be installed and then surveyed, and that survey given to the skin guy so he can manufacture the skin to fit. Now, the general contractor in his wisdom said, well, I have this model. Why don't I give it to the fabricator and give it to the skin guy, and they can both do the fabrication to this model, and what we'll do is we'll survey the structure at noon when everybody's at lunch so that we can tell where the structure is. All right, well, quick thing back. On the Hancock building, during its structure, as it was partially that way, during the day, that structure would move 8 inches away from the sun. The side was heated, expanded, side back it, that's under shade, stays there, and so that structure bows away. This structure here, under these at noon, when in Chicago, at 85 and 90 and whatever degree temperatures, we're talking as much as we found in our model, the modeling of it, 8 to 12 inches of movement of this structure, and they are supposed to be surveying it to determine where the skin's going to fit. How many here believe it fit? They managed to get it in, but it was an issue. Specified tolerances. The AISC Code of Standard Practice has tolerances in there. They satisfy a 4, 5, 10, 15, 20-story building really well. Beyond that, manufacturing facility, anything like this, cantilevered arenas, stadiums, there aren't any. Now, as they said in the specification in one of the presentations earlier today, that if a tolerance is not in the AISC code, it does not mean it's 0. It just means it has not been specified. But does that impact loading? Absolutely. Deflection criteria. Oftentimes we'll get involved in scenarios where we have a deflection. We're going to be loading the structure, the loads in the structure. We're going to be putting compression on tension members. We're going to be putting tension on compression members. Some engineers get a little testy about that, a little concerned. How are we doing it? And the issue will be is actually in most structures, in arenas and stadiums and those sorts of structures, during the construction, we'll move the dead load around. It will not be, in the end, exactly as the engineer had expected it in his modeled structure. That can be an issue. So we need to have information from that with regard to if they have erection concerns or elevation concerns, things that need to be done. So I've talked enough now. I'm out of stories. I'm introducing Jeff, and Jeff can come up and carry the ball.
Do you have a few quick questions before we let Jeff take the ball? Yes?
Just very quickly, David, in your early slides, you were expressing concerns about responsibility and lack of clarity.
Yes.
I should refer everyone to Code of Standard Practice Section 1.8, very specific on the responsibility of EOR, the structure, and the erector. But Section 1.8 of Code of Standard Practice.
Thank you, Mike. Yes.
Another one of your slides, you were talking about the difference between 600 base shear versus 130 base shear, and you kind of said, well, you really don't design to the 600, but you also, well, what do you actually design to?
Well, sorry, Dave, could you come in, because it's being recorded, so you need to just repeat the question and then provide the answer.
The question was on our slide concerning the base shear of about 160 some, but according to ASCE 3714, it would be 608. What we're saying is that 608 was on a bare structure that was bare the entire 5, 6, 7, 8 stories. The likelihood of that occurring slim to none. But on the other hand, if you're the erection engineer, that's something you really want to talk to the erector about. Because if in fact you're in a project where you are working for the steel erector, but the metal deck installer is somewhere else, then there's an issue here as to what is the schedule for that other coming in place. But you need to know that early on, because that's a major bracing issue. Is that clear?
So, I mean, basically, you have to, it's a case by case, it's a gray area that you have to work. It's not,
absolutely.
It's not defined by the...
No, it's not defined.
You have to work with the people you're working with.
The one thing I found, I told you, erection engineering was a lot of fun. The reason why is not cookbook.
Yes.
So, in your experience, what happens when the engineer of record hides behind the specs and they don't give you the information exactly as you said?
Can you repeat the question with other words?
Okay.
Specifically now that you have architects who are coming up with these crazy new beams, unusual stadiums.
So you're asking, well, how do we handle an issue where we are not able to go into an agreement with the engineer or the architect on the scenario as what it amounts to? Not all the time is it pleasant. I know that we rented in one at the University of Illinois where the engineer response back after we went through this whole question with regard to a building that had moment frames on the exterior walls, bracing on the interior walls, 3 stories tall. When you run the analysis, the bracing is so stiff the moment frames never get any load. So we said, we'll just get rid of the moments on the outside. We did all that good stuff, changed the thing, and got back to meet with him. And he said, well, I'm not comfortable doing that. And I looked at the owner, because we were talking $400,000. It's amazing how money talks a little bit. And I just looked at him and I said, you know, I'm sorry. I'm not here to embarrass you. I'm not here to critique. And say what we're here today is because this project's over budget. And this will save $400 and some thousand. And personally, if you're not fuzzy, warm about it, I don't really care. Now, there was then a kind of a knock at the table, and the owner said, engineer, we need to have a conversation. They left, and they came back 45 minutes later and said, Mr. Ruby, we will proceed with all of your recommendations. Put this down, this down, this down, this down. What happens here is that it can't be an ego thing. What I find most of the time when there's been that conversation with an SER is that he does not have or has not been exposed to what engineering is really necessary to build the building. And because he doesn't understand that, that's an area of ignorance in his so what he tries to protect that by insisting on going in one direction without sitting and learning. But what I find my question would be is when I was answering the question a little briefly, when I was working in Chicago in the 60s, and we worked for SOM and a dozen other firms, and I will tell you, I was with American Bridge. We met with SOM at least once a month on a project. They would bounce off ideas, concepts, et cetera, with regard to it. And what we found is those that know, ask, and those that don't. And I don't, you know, the question would be is the issue I would say with most of the time it's been an issue is that we've managed to get some smoothing by putting some what saving this is taking place. But it is a difficult issue. I agree with you. It is.
Another question?
Yes?
thought I saw a hand. Was it a shy hand? That's
A shy hand?
Quite make it up.
Yes, sir.
Just a brief comment. I've worked for a company for a number of years that did thermal power plants. And you often have, that you can't get all the equipment into the building if all the bracing's up. So they have an expression, leave out steel.
Yes.
They'll leave steel out.
Yes.
Until they get the equipment done, and then they'll.
Right.
put the bracing.
Yes, sir.
Something engineers, if you're working on a thermal power plant, look out for that.
For leave outs. Oh, yes, absolutely.
Yeah, you've got to see
Yeah.
where that equipment's going, how you get it in.
That's,
Do you have a comment on the sequencing and some?
oh, yes, it is, very much so. It's very much so. We have done a few of those power plant issues, actually, for the erector, when they weren't necessarily designed to have the leave outs left out. And so what we've done for them is to work a sequence out with the equipment people, the erector, and try to minimize any additional bracing that we would have to put in. But we have to engineer that one piece at a time. It's not a cookbook solution.
Okay, thank you. We'll have time for one more.
Yes, sir.
One more.
Is there a possibility that you go with a design assist solution where an erector / construction engineer is now involved in the design? And because in bridge engineering you have, like you just said, you have deck sequencing, you have full sequencing, an erection sequence, like that. But you don't have that in buildings.
We need about 45 minutes to talk about that.
Okay. What are your comment on the design assist?
I would say is that my comment on design assist is who perceives it to be what? Is it actually the fabricator finding a way that he can get into the project a little sooner to kind of give himself a beneficial advantage? Is it, from the engineer's point of view, is it a way for him to say, okay, I can let some of this design responsibility slide down to the fabricator's engineer or this design assist guy, and therefore he becomes part and parcel of the total responsibility for the project, which actually in fact is happening, when in fact that's not really the intent, but that's really what takes place. My feeling would be a design assist. I understand why it would go through a fabricator, but my feeling is the design assist would be better if it was brought on board by the CM or the owner, or as a second, third-party audit of what's going on, so that it's not, well, it's not creating another entity part of the part. So that's my experience, and I've done design assist since 1964, 65. We were doing it before it was in vogue. American Bridge did it all the time. They gave it away. They gave all the engineering away to anybody, whatever it is, so they could fabricate steel. They're not in business now. I've got a reason. All right? Thank you.
Thanks, Dave. So what I'm going to do here is I want to give just a brief talk, ASCE 37, how we use it as erection engineers, talk about some of the equations regarding construction period wind development, and then give you some typical pressures that we find as erection engineers, give you and then some case studies of a few different design elements. So first, what does ASCE 37 tell us? Well, it tells us if you want to develop wind, go back to ASCE 7. So here we've got our force equation. Force is equal to the pressure times the area. We've got a couple other extra variables here. The gust effect factor is typically 0.85 when we're doing erection engineering on structural steel jobs. And our force coefficient, which is a function of the area of steel to the greater whole. So that particular factor can be anywhere from 1.6 to 2, but more often than not, as erection engineers in our office, we find that's 1.8. So this equation here, we're going to investigate the pressure, but G and C sub F, they kind of stay typical 0.85 and 1.8. Then you have the area of the steel. So that's, as Dave mentioned earlier, that's all projected surfaces of structural steel. So it's normal to the wind and can be quite substantial, as Dave noted. So as we investigate the pressure a bit more, we have this equation, 0.00256, a couple different K factors, and then V, which is the base velocity of wind. And the big takeaway here is that that particular value is squared. So all the engineers in the audience here have seen this many times, but the big takeaway on this one, that V squared, if we're talking about a 10-mile-an-hour wind on a job site versus a 100-mile-an-hour wind on a job site, that's not 10 times the amount of wind, that's 100 times the amount of wind. So that pressure exponentially gets quite large. So again, with ASCE 7, here's the wind maps. What ASCE 37 tells us is during erection, we can use the risk category 2 maps. So these maps had changed in 2010. They're now given an LRFD, which means they're load factored. So if everybody that's been around for, more than the last 6-7 years and used the old maps, these were 90-mile-an-hour wind zones was the primary focus of the country. And then as you get out of the coast, those pressures go up, or the wind speeds go up and up. So that 115 is an LRFD load. What we do in order to communicate with our clients is we convert that back to ASD. It's on our drawings, we're trying to communicate with real world wind speeds. So the anemometer at the top of the crane boom does not measure with a load factor to get you to LRFD. It's talking real world wind speeds. So we convert that. And then the last thing that we want to take away from this particular slide is, and Dave talked about it, was through ASCE 37 hurricane. So there's about a 4-month period where we're outside of hurricane zones along the coast. With ASCE 37, we're allowed to take that base velocity and use the 115. So again, convert it back to ASD, but for that 4-month period, erection engineers, we can use that lower 115 miles an hour as our baseline. For the 8 months that we are in the hurricane season, you have to have that contingency plan. And that contingency plan, taking Miami, for instance, which is, LRFD again, is 180 miles an hour, that pressure could be 200 times, meaning 200 times the amount of temporary bracing that you're going to be required when you're making that plan. So just as a heads up, it's better to build when you're off season. Dave talked about really what did ASCE 37, what are its takeaways, where did it all come from, where's its basis. The biggest thing that we as erection engineers use ASCE 37 for is this handy little reduction factor. So what this reduction factor is talking about is based on the duration of the project, you don't have the same probability that those design winds will be on your structure because of the duration of the project. It's just a function of probability of the wind hitting. So in our office, we find that most structural jobs that we do, I'd say 99 out of 100, and it's probably 100 out of 100, we fall in the 6-week to 1 year. So ASCE 37 has given us a break of 0.8 on that base wind. So at the bottom of the screen here, what we have is just talking about the base velocity. So we take the new map, 115, which is LRFD strength. We convert it by dividing by 1.26, which is a value that ASCE 37 gives us. And now we're back to, it's 92 based on that factor, but we're really back to the old 90-mile-an-hour wind maps. So now we multiply that so during a construction period, so temporary wind loads, we multiply that by that 0.8, this is the reduction factor they gave us, and now we're back to 73. So the reason I did this is I wanted to say, as erection engineers, when we're doing work for an erector, generally we're bracing up that structure for 73 miles an hour on most projects, and then providing some factor of safety on top of that. So what I thought I would do is put this little table together here, and what we're looking at is A couple different heights, so exposure B or exposure C. This is most projects that we run across are in those two exposure categories. But what you can really, the big takeaway here is seeing just how quickly that pressure goes up. So what I've done is I've used the equations that we previously ran through, and then just plugged in 6 different velocities, and develop these pressures. So you can see just how exponentially quick that pressure builds once you get higher and higher wind speed. So, if you have a 10 mile an hour out on your job site, that's a relatively windy day. You might lose your hard hat. You're talking 25 miles an hour, you're starting to think about shutting down the crane. Well, 10, 15, you're at 1 PSF. I mean, that's nothing on your structure. 30 miles an hour, you're shutting down the crane, you're still under 5 PSF on your partially erected structure. So, like I mentioned, ASCE 37, we're designing and bracing, analyzing to the 73 miles an hour, where if we were talking about LR or ASD, just the full design, the lateral load resisting system, the completed structure, that's up there at 90. So, just taking a look, at 90, we're designing to 20 to 35 PSF, so it's a pretty sizable load. So as I was preparing for this, I thought, it would be nice to show everybody, just give them an idea of what velocity equates to in pressure. I mean, the table was nice, but you couldn't put your hands around it, you couldn't feel it. So 2 weeks ago, across most of the Midwest, we had this nice windstorm that kind of provided an example for me. What you see in the photo here, this is the outage maps from DTE. DTE is our energy provider, and those are all the homes that lost power that day. It's 60 to 65 mile an hour winds. I've been in the Detroit area now for 20 years. That's as high as I've seen it. We lost power to 1 million homes, nearly 800,000, and we had a power outage for roughly a week for a lot of homes. I think we had one guy in our office just got his power back last Saturday. So it was pretty devastating, but it gave us something to look at. So I take that 60, 65 miles an hour, run it back through our same equations, and equate it to a project. I thought about it. I'm like, well, all the damage that was occurring was really from trees knocking down power lines or falling on this poor guy's car, tearing off awnings and what have you. But the pressure, whether you're category B, category C, you're still in this 9 to 13 PSF. That's half of what we're designing structures for on the full. And then if we convert that in running that to for an erection engineering job off that 73 miles an hour, that's about 65% of the design load is really what we're designing or analyzing structures for temporarily. So now we've got just a couple of the case studies I wanted to show you just really how wind can impact some jobs. So first we just start with this freestanding column. The column's 45 feet tall. We put our wind pressure on it in the 10 to 14 PSF range, exposure category B. And you can see we generate overturning moment at the base of 15 kip feet. That's not a lot. But when you look to the bottom right of the screen here, you see the base plate, and you see this 6x6 base plate pattern. It's a 6x6 anchor bolt pattern, sorry, and it's a 24-inch by 24-inch base plate. So it looked a little weird. The anchors are 3/4 inch diameter, A36, and now we're applying the 73 miles an hour wind pressures of 10 to 14 PSF. So the one thing to note here is the erector wasn't using shims. So now we're on leveling nuts back on that 6x6 pattern, back with the A36 threaded rod. Needless to say, the anchors don't work for the ASCE 37 wind loads. We're in overstressed. We haven't quite failed, but we're getting there. Well, this is what it looked like when I got to the job site. That's the column. You can see the great big base plate pattern. Fortunately, or maybe unfortunately, depending on how you want to look at it, this did not fall from wind. This column fell due to an incidental load during erection. So what happened was, during fit up, they were trying to tie in up at the top of the column and just trying to force fit a girder into the column. Again, that sitting on those leveling nuts, there was hardly any resistance. So what you see there is, 3 of the 4 anchors are still at least on the base plate. The other one shot off to God knows where. But you have this tensile rupture. And when I arrived on the job site, and first thing I asked the guy is, where's the shim packs? You have this 24-inch base plate. You got all these opportunities to throw some shim packs around. Where are they? We didn't think we needed them. So I thought I would just, for the purpose of this presentation, kind of back solve on this 45-foot column. At the time, we were brought in and gave them some erection engineering services to tell them where to put some shims and where to brace, etc. But for this presentation, I thought, well, let's figure out what that 500-pound load at the top of a 45-foot column, what does it do? So it's an incidental load. It could be a beam off the crane colliding with the column. It could be the boom rubbing up alongside the column, or it could be, and this is probably the biggest one, is just fit up. So if you had a braced frame and you were trying to fit the girder, the adjacent column, you're trying to fit the girder to the adjacent column from a braced frame, the braced frame's not going to go anywhere. But if for whatever reason it's long or tight and you start putting in the drift pin and the iron worker gets out his beater and he starts getting after it, 500 pounds you can get there in a real big hurry. So I think you all know where this is going. Just 500 pounds would generate a moment of 22 kip feet. These anchors give way at 19, so no bueno. Our lessons learned here, for the erection, or for the engineers out in the audience, push out those anchors whenever you can. Take them outside of the profile of the column. It affords a lot of insurances during erection. And if you need a 24-inch by 24-inch base plate for some reason, question yourself as to why you have a 6x6 anchor bolt pattern. If it doesn't look right, it's probably not. Erectors, leveling nuts are great, but if you think about what they're doing, you can't be putting a dead load on them. You have a nut underneath the base plate that's now taking dead load, so it's as good as those threads that are engaging that anchor bolt. On top of that, you enter any amount of overturning moment into it, it's recipe for disaster. So add shims. Very cheap insurance policy. Look out for forecasted winds. That's if you have a good plan, you shouldn't have to worry about it, but keep an eye out on it. And then just, be aware of those incidental forces. If you see guys beating bolts or beating drift pins in place, take a look and make sure you got some shims down there for some way to resolve that moment. So our next case study here, this is a very, very lightweight manufacturing facility. Exposure category C, which means it had some increases in wind. It was probably arguable. It could have been B, but that's what the general note said, C. This building is roughly 80 feet tall. There are no intermediate floors, wide open spaces, 50 by 50 bay. And we were asked to provide a stability plan for it. So we started analyzing it. 80 feet, you're probably talking 20 PSF on the structure. So, through typical methods, we're putting in wire rope bracing where we can. And then we noticed this 6x6 foundation. I said to the engineer my engineer was running the numbers. So this column is 80 feet tall. It's sitting on a 6x6 foundation. It's 18 inches thick. That foundation weighs 8,000 pounds. My first thought was, we're going to pull these foundations right out of the ground. Well, we got into it. We did what we could. We put in our, came up with a bracing plan, found we had about 18 kips of tension force in wire rope bracing. Like I said, about 20 PSF at that 80-foot roof. So that brace has about a 12.5 kip horizontal component. We didn't pull it out of the ground, but it would slide if it were subjected to ASCE 37 full wind loads. You know, the only thing that's there to resist it is the sliding friction resistance and a little bit of passive earth pressure on that 18-inch face. So as you see there in the numbers, we had, from our brace, we figured 12.5 kips. We had determined we had an ultimate lateral resistance of around 9 kips. So back solving that for, okay, what are we good for? Because we're still just going to use these foundations to resist this this structure and keep it stable. We found that we had about a factor of safety of 1 at 60 miles per hour. I mean, we talked to our client about that. Said, hey, you know, if there's forecast winds greater than that, you know, let's talk to each other and see what we can do, because it's going to be interesting. We got lucky. Lessons learned here. Make sure these extra tall columns with no intermediate floors, they have a decent foundation. You know, if you just draw that to scale, 80 feet tall, 6 foot wide base, I mean, it doesn't even look right. So again, if it doesn't look right, it's probably not. Sure, it works great in the final structure, but you know, keep your erector in mind, keep erection in mind. This structure was a great big roof diaphragm, took loads to external braced frames, but in the meantime, you know, there's a temporary load path, temporary stability to be thinking about that the erector has to contend with. And erectors, you know, look at those foundations when you're bidding the job. Understand that you have the ultimate responsibility in keeping this thing stable. And if you're going to be tying off to the bases of columns, understand what the base of that column is sitting on as well. So our last case study here, this is kind of this one's been around in my repertoire for quite a while. Some of the guys in the audience, I'm sure, recognize it. He's shaking his head. This is a very lightweight industrial facility. I think this building is about a half a mile long. 1 mile long. 1 mile long. That base space is 100 feet, and then the short direction, that's a 40-foot column spacing. That's not an optical illusion. Those first 5 columns have about a 4 to 5 foot sweep in them right now, and this is our client was starting the job and had a mile to go, and here's where the first 5 trusses ended up. So they gave us a call and said, hey, can you help us out? We said, absolutely. Send us the drawings. Then we started looking at the lateral load resisting system. This system has a roof diaphragm. Like I said, the joists are 40-foot joists, but to deliver that diaphragm load down to the vertical braced frame, strangely enough, it relied on the columns to cantilever from the bottom chord up to the top chord. So you kind of had this tabletop of diaphragm and relying on the bending resistance of God knows how many columns from the bottom chord all the way up. It had a real light bottom chord bracing system, horizontal, the bottom chord, and like I said, the vertical braced frames. So we started looking at the challenges throughout the drawings. I said, all right, well, they've set a couple trusses. It's 100 feet long, but the truss has a 8-inch wide top flange. This was a double negative. Number one, the 8-inch top flange, when you go to set the column, is not the 100-foot unbraced length. The compression load generated in just setting the column is too great for that cord to handle. So now you have to set additional members back to cut down the unbraced length in order to cut free from the crane. The second problem with the 8-inch top flange is when you start talking ASCE 37 and put your 73 mile an hour winds, so at this height maybe we're talking 20 PSF, we have no real way to bring it back to the column lines. The issue here is the weak axis bending of the top chord just isn't there. This building has no sway frames, so we get no help from the bottom chord, and we still need to figure out, all right, how we're going to get it to that braced frame. Well, one other thing to note on this drawing, so this 40-foot joists, these 40-foot joists, you know, they have very limited compression capacity, and if you look at the column line, at the top chord elevation, that's also a 40-foot joist. So from an erection standpoint, we're trying to bring load out to the braced frame, but at the top of this braced frame, we have a 40-foot joist. That's good for probably 600 to 1,000 pounds of compression. So lots of challenges. What we ended up doing, so to provide stability to the top chord, we added temporary sway frames to work off of the bottom chord. And then we ended up adding a horizontal bracing system. This is all done in wire rope. And we had to put that in there temporarily until there was enough deck in place that we could cut it free and get that diaphragm action. Going back to that joist that I was talking about, the 40-foot joist that's on the column line, when we, what you see here, we probably added that every 5 to 6 bays in order to deal with the wind loads. But when we bring it out to the column line, the biggest problem is we still don't have a compression member. We don't have a member out there that can take the brace force. So we had to brace the columns on the column line, not so much because there's a braced frame there. So you're thinking, why temporarily brace at a braced frame? Those wire ropes are in place in order to put that whole system into tension. So because there was no way to get the horizontal load to the braced frame, or to the vertical brace frame, other than keeping the load out of that 40-foot joist. So the job went fine after that. Got those first couple bays up, and once we got the plan rolling, client made it through the whole mile, but not without these challenges. I mean, I'm sure that this amount of this false work, the wire ropes that we're talking about here, temporary sway frames, adding temporary horizontal braces in order to deliver load, none of this is going to be in their number for sure. So the big takeaways on this one, as an engineer, think about that truss size, that truss top chord size. If it's a wide flange, try to turn it so that the web's horizontal. We get significantly more bending capacity, significantly more axial strength when that truss top chord as a wide flange is turned horizontally. And even though everybody's looking for these light structures, or at least it was en vogue, but it doesn't necessarily mean least cost. So, if you think about the labor, erection, the time, everything else that's going into it in order to make this ultralight structure, stable temporarily. And then on those column lines, think about the erector, think about erection. When you have a joist on the column line, upsize that. Get a wide flange in there, something that can take some sort of compression load. And think about truss stability. Understand that when these erectors are doing these types of jobs, that those roof diaphragms, they might not be in place for 3, 4, 5 weeks, and that's just for a given bay. So and as a job is sequenced, you might not be engaging braced frames for quite a while. So there's a lot to consider there. And that the big one is, these lightweight buildings aren't necessarily least cost. As the erector, this probably is not a surprise, but don't be basing your bid off of tonnage, especially that one, lightweight. So if your number is based on that tonnage, you're going to take it on the chin. Look for that lateral load resisting system itself. Per the Code of Standard Practice, Dave touched on it. It should be given in the general notes. It's normally not, at least the drawings that I've seen and we've all probably seen. But if it's not, you can ask the question. Just ask it as an RFI. Fire it back at the EOR. What's the lateral load resisting system? Both directions. We're just looking for it. Nice to know. Watch out for, this is kind of like the tiny little foundation. Just keep your eye out on joists on column lines, small foundations, just those little things, because as erectors, you're needed to provide that temporary path, and you're responsible for stability throughout. So look for the weak links in the chain if you can. And with that, I think Dave wanted to talk about a few things on... Sure, here comes Dave again. Thank you.
Before we go to the conclusions, do you have a few questions? Yes?
I know it's not a hard and fast calculation, but what's the rule of thumb that you use when if you're a director, you're looking at a job, you're looking at that truss top forward, you're looking at the width, and you're looking at the length. I know you guys, there's a rule of thumb you use where you got to take a harder look at it to determine if it's going to need some temporary support while you're erecting it.
Yeah. So Dave taught me, or somebody repeat the question. Okay. So the question was, as a rule of thumb, when will an erector have some heartache with trusses to set them, to cut them free? So this is kind of a unbraced length question. And what Dave taught me a long time ago, and this probably came from American Bridge, and is you take the span in inches, so it's L over B. Your span in inches over the width of your flange. And what we said is under 80, if that value is under 80, you're probably okay to cut free the crane. If it's north of 80, so 80 to 100, you're going to want to look at it. And then what we tell people is if it's greater than 100, give us a call.
Yes.
It's maybe a little off topic, but on your second example case study there, you had a case where the structure was failing and wasn't going to pass the loads. So you had to address the customer at some point about what's the probability of us getting 60-mile-an-hour winds, what's the likelihood of this happening, and if this does happen, this whole thing could fall over. How do you guys address the probability of that happening and talking to the customer, so that way they have a frame of mind of all right, what risk am I really taking, and how do you make sure that they are accepting the risk and you're not culpable of anything going on?
All right, so the question was in regards to projects where we can't sufficiently brace to ASCE 37 loads. So on the example that I showed, like I said, we had a factor of safety of 1 at 60 miles per hour. So the question was, how do we deal with managing that risk? And how do we, as far as the probability goes of wind speeds being higher than that, so what we told her, so let me back it up. So what we told our client on that job is, hey, there's an issue here. We don't have enough structure to really hold this thing down until it's complete. But we know you're okay into, say, 40, 42 miles per hour. We're happy with the factor of safety. At 60 miles per hour, this thing might start sliding, and you'll come to the job site, and it might be, you might skid the job over 1.5 inches. I don't know. So, what we did on this particular project is that we just informed them and said, hey, this is a risk management situation where you're going to have to manage your risk. Otherwise, you're going to have to externally brace this structure to anchor it down. Now, I know there's means of doing it, but in this particular case, you asked about the culpability of it. All we could do is inform them. We gave
case by case. It's a case by case, pretty well.
Well, I'm not sure I understand what your question is.
No, but I mean, like every case seems to be different. It's hard to have a general rule for this.
Oh, right. There is, there could be a number of different things that, that's that weak link in the chain. For this example, it's not often that I don't think I've ever run across this. This was the first one that it said that there wasn't enough foundation on the job to anchor us. So it doesn't happen often. Just generally there's enough structure, there's enough foundation and concrete and things to tie off to resist that ASCE 37 load. So, like I said, we brought it up. We told them that they're good up into the 40s. I think it was the middle of the summer when they put it up. We never had an issue with it. They managed their own risk, and we were on the red phone if winds were coming.
Okay, thank you.
Any other questions? I was going to say one thing that, in answering your parts of that, adding to what Jeff had said, we have taken to the time to where we have actually gone on and looked at wind records, wind direction, the maximum wind, what direction is it coming from, what months was it in, what was the probability. So there's a lot of that. When we go to the owner or the contractor, we just didn't go and say, oh, well, you got a problem, what are you going to do? We went and discussed this whole scenario. What was the possibility if, in fact, we were at factor of safety 1 at 60 miles an hour? What do we believe your risk is? And we thought it was extremely low. But we gave them the basis of what we were talking about. Okay? But I understand. The question would be, I guess I can add the thing, which you didn't ask, but what kind of criteria did we use when we were erecting the Hancock building? What manual did we go to? What published documents did we look for? There weren't a lot of 1,000-foot tall buildings those days, and there just wasn't anybody to tell us which way we would do it. And really what happened, we sat down, and I had the pleasure of sitting down and spending several weeks with Fazler Khan. And we talked about what were the options. And the biggest concern they had, because they weren't concerned about the building, they could make the building what they wanted to be, but they were concerned about the perception of individuals. What do you feel when a building moves? And what movements are perceptible? And there was some studies done in the 40s, that was in the last century. ASCE did some. We talked about the fact that if you were at, I think it's 0025, that's what I remember, that is pretty safe. 003 is on the fringe, and if you're 0033, your secretary will start to throw up. Now, so Hancock was pretty much based on 0025, as that was their ratio of deflection to story height. But what we found when they were doing it is that the lower floors of that are office buildings, and around the 41st or 42nd floor there's a double floor, which is a mechanical, and above that there are apartments. And so they had some model apartments. Now, there's not a lot of people here, I think, remember swag lamps on a chain over a table. Your grandmother had them. So in the apartment, in the model apartment of the Hancock building, up around 44, 45, close around 50th floor, they have some model apartments. And while they're sitting there with this model apartment, it's all furnished, and they got people walking through, and here is the light over the table that's just doing this. And the girl that was working there was getting sick. And so what they did is they took the chain, the swag chain lights down, and they put a solid rod from the ceiling right down over the table. Doesn't sway anymore. So there's always ways to get around those particular scenarios. But we're talking about this. I hope what you want to say today, what we were truly attempting to do today on this A37 is understanding that there's two sides to this story. There's the structural engineer of record, and there's the erector. And they are not enemies. The structural engineer knows a lot of information about the structure that the erector doesn't know. But the erector knows an awful lot about installation and how you erect it and procedures and methods and procedures that the engineer thinks he knows. So what we want to try to do is to understand between the two of you that there is this reason to come together, because the structure is the purpose of the end, not the drawings, but the structure is what we're looking for. And we were hoping that what we given today, a little enlightenment on both sides, from the structural engineer side, but also back to that there's concern on both sides of the table. So when they're asking you that question, they're not asking you to be annoying. although it might be an annoying question. But when they ask you the question about what's the lateral load resistance system, they said, well, you mean I have to tell you how to build it? So, no, we're not asking you how to build it. What we're asking is, what is your lateral load resistance system? So we get that note that we had before. Well, that doesn't tell me anything, because I don't know when those precast panels are going to be put in or when the deck's going to be put in. So I need a little more information. So just understand that it's an issue. And I guess I would look at this. For all of you who have children who play with Legos, you look in that, they all have instructions in there. There's actually an instruction how to put it together. Now, when you do your design, you don't give anybody instructions on how to build it. It's not for you to know and them to find out. It's for you to share. Thank you very much.